Welcome folks. Calculus 2 video describing another application of integrals. In this case, we'll find volume by the method of discs or washers. Similar, just a little bit different. So again, this strategy highlights what we've done before, that we're seeking to find a quantity. We'll approximate that quantity with a finite quantity, add up all of those finite quantities to obtain a Riemann sum, let n go to infinity, and that Riemann sum becomes a definite integral. In this case, however, though, we're not going to explicitly write down the Riemann sum like we've done before, so we'll go ahead and just think about things in terms of little bits of area. We'll see what we mean by that in a minute. So the main problem here is that we will be creating a solid by revolving some region around an axis. In this case, we see that the region is the area between the x-axis and the curve f on the interval from A to B. Revolving that around the x-axis, we obtain a solid. Our goal in general here is going to be to find the solid of that of revolution, find the volume of the solid of revolution. And our strategy is going to be thinking about taking a little slice in some direction. In this case, we'll start off by using the x direction and then trying to see what the volume of that slice looks like. So again, our general strategy here will be to take a slice with thickness dx or maybe dy. You can see that depicted here. We'll think about identifying the volume of the solid obtained when that slice is rotated. I'm going to refer to that as a bit of volume. And then we'll use the definite integral to add up all these little bits. So we'll illustrate that with an example. Here's the first example. Let R be the region bounded by 2x minus x squared in the x-axis. And let's find the volume of the solid created if R is rotated about the x-axis. Okay, again, here we start with a curve that's a parabola opening down. And the x-axis, of course, that parabola is bound between 0 and 2. So the region that we're set to revolve is the region, again, underneath the parabola, between the parabola and the x-axis on the interval from 0 to 2. So again, revolving this region around the x-axis, we'll try to identify the shape we get when we revolve a little bit, a slice in the x direction with thickness dx. So you can imagine that revolving a slice like that will give you some sort of circular disc with a little bit of height to it. I'm going to call the volume of that little disc dv. It has a radius I'm going to call r and a little bit of thickness dx. So the volume of that disc, therefore, is pi r squared times its thickness dx. Now in this case, the distance r is just given by the distance from the x-axis to the curve. So that ends up just being 2x minus x squared. This gives us the volume of our disk in terms of x, that is dv equals pi times 2x minus x squared times dx. And having it in terms of x is important because we've taken a thickness with thickness in the x direction, so we're going to want to have all x's in our quantity. Now we'll just use the definite integral to add up all of these little bits of volume on the desired interval from 0 to 2, and that'll give us the volume of the corresponding solid. So again, writing the volume dv as pi times r squared dx. I think I forgot that additional power of 2. We see that the volume v is the integral from 0 to 2 of pi times the quantity 2x minus x squared all squared dx. Expand, use the fundamental theorem of calculus, evaluate at 2 and at 0, and away you go for the volume here, 16/15 pi units squared. The same strategy is useful in a slightly different situation when instead of obtaining a washer, instead of obtaining a disc, we might obtain a disc with the hole punched out, or in other words, a washer. So to motivate the washer example, we'll think about revolving a region bound between f and g on the interval from a to b around the x-axis. And you can imagine that similarly, if we put a little slice dx in and think about the volume that we get by revolving that slice, we end up with something that has a hole in the middle, in other words, a washer. So in this case, again, the strategy is to slice with a little bit of thickness dx, add up all of those little bits of volume with the integral, and use the definite integral to evaluate on the given interval. So we'll illustrate the use of this strategy with an example. Here's the example. Let's think about the region bound between the curve 3x minus x squared and y equals x. And we'll try to find the volume of the solid created when this region is rotated about the x-axis. Again, here we have a curve that's a parabola and a curve that's a line. So you can see that the region in question is the region bounded above by the parabola and below by the line. We'll go ahead and revolve this around the x-axis, thinking about the volume obtained from a little bit of thickness, again here, dx, revolved around the x-axis. As you can imagine, when you do that, you're going to end up, again, here with a washer. So I'll go ahead and sketch that washer, and then we'll think about how to find its volume. So we see that the volume of the washer is defined by the difference in two disk volumes, pi times an outer radius squared dx minus pi times an inner radius squared dx. Now, of course, the inner radius is given by the distance from the x-axis to the line. The outer radius is given by the distance from the x-axis to the parabola. Substituting those in, we can get an expression for our bit of volume dv. In this case, the inner radius is x, the outer radius is 3x minus x squared. So the bit of volume dv, and I factored the pi to express it as pi times the quantity, 3x minus x squared all squared minus x squared dx. Use the definite integral to add up those bits of volume on the interval from 0 to the intersection point. In this case, we can see from the graph that that intersection point is at x equals 2. If we weren't sure, of course, we could just set the graphs equal to see where they intersected and just use the fundamental theorem of calculus to evaluate the corresponding definite. So again, here I'll omit some of the details on the definite integral, expand the quantity 3x minus x squared all squared, simplify under the integrand, pull out the pi, find some antiderivatives, evaluate between 0 and 2, and you find that the volume of the region created by revolving, the volume of the solid created by revolving the region around the x-axis is 56 over 15 pi cubic units. Okay, some variations on this theme include the following. Variations might include revolving a region R around the y-axis instead. In this case, we'll have to be sure to slice with thickness dy or delta y. And also you may encounter problems where you want to revolve a region about an axis that's parallel to the x or y axis. And in this case, you just have to be a little bit careful about how you compute those radii. So here's the first example. Let's think about the region R between the y-axis, the line y equals 1, and the line y equals the square root of x. It's pretty straightforward to sketch, so we'll go ahead and do that. The x-axis, the y-axis, the curve square root of x, and the line y equals 1, and the region between those. So this region in blue. We're going to go ahead and rotate this time around the y-axis. We'll see that it's going to be handy to use a slice with thickness delta y or dy instead. So here's our slice with thickness dy. You can imagine that when you rotate this around the y-axis, you're going to obtain another disk, except this disk sits flat instead of sitting upright. So here's a sketch of the disk, and we'll go ahead and find the volume of that disk in terms, in this case, as we'll see, of y. So the slice, the rotation about the y-axis, the generation of a disk with some radius r and some height dy, the volume of that disk dv equals pi times r squared times dy. Now, unlike the previous examples where we sliced with thickness dx, in this case, slicing with thickness dy tells us we want everything in terms of y instead of in terms of x. Of course, the distance r is given by the distance from the y-axis to the curve, which happens to be exactly x equals y squared. Expressing the bit of volume as pi times r squared dy gives us the bit of volume dv is pi times y squared squared dy. And then we just use the definite integral to add up all of those bits of volume on the y limits, as it turns out, from y equals 0 to y equals 1. So again, adding those bits of volume from 0 to 1 gives us the integral from 0 to 1 of pi times y to the 4th dy. Use the fundamental theorem of calculus, evaluate at the endpoints, and we obtain 1/5 pi cubic units for the volume. Okay, one final example, let the region R be the region between the y-axis, y equals 1, and y equals the square root of x. In this case, we're going to go ahead and find the volume of the solid created when the region R is rotated around a different line, in this case, around the line y equals 1. So you can imagine that in doing that here, in this case, we're going to obtain a disk. However, the center of the disk is not on the x-axis. It's on a line parallel to the x-axis, again, in this case, given by the line y equals 1. Okay, so we'll go ahead and sketch that slice again. Think about the volume of the corresponding disk, and then think about the integral generated by adding up all of those volumes on the given interval in x. So again, the volume of this disk is going to be pi r squared dx. And in this case, r is exactly the height of that slice, which is the distance from the line y equals 1 to the curve. So 1 minus the square root of x. So when I talked about computing the radii carefully, this is what I meant. You can imagine that the distance from the x-axis to the purple line is 1. The distance from the x-axis to the blue line is the square root of x. And we're interested in the difference of those distances. So 1 minus the square root of x for the radius. Just use the definite integral now to add up all of those bits of volume on the interval from 0 to 1. So we end up with the volume as the integral from 0 to 1 of pi minus the quantity 1 minus the square root of x squared dx. Expand the integrand, use the power rule for antiderivatives, fundamental theorem of calculus, end up with 1/6 pi units cubed for the volume. Okay, folks, hope you've enjoyed this video on discs and washers. Have a great day, and we'll see you next time. Bye-bye.